I don't think so. There isn't like something I sign that says you need to be saying this, that, or whatever. It's kind of crazy. I mean, in post-secondary education, what we're in right now, right? In high school, middle school, elementary school, right? There's curriculum that the teachers have to teach all this stuff. Here, I can do whatever I want, which is nuts. I thought there'd be like, you need to be talking about this, and this. No, you're going to teach them mechanics and materials. This is our little excerpt of what they're going to be learning. It's kind of whatever I want to do. It's kind of nuts. So much power for one person. Anyway. Okay. So, as I did mention, good news. No assignments for Halloween weekend, which apparently people, love that, right? You guys all 21, right? No?
Yeah.
Transition? Nice. So, maybe you do enjoy that. No homework or a quiz this week, just because we did our review. We finished that up on Friday, and then we're going to continue starting to talk about beam bending, right? It's kind of our last big component. We did axial loading, torsional loading, and now we have bending, right? We talked about beams and how critical they are and how common they are in structural systems, okay? And so we're going to look at the mechanics behind beams. So we went through our little review of Chris Allen, right? And all the incredible wisdom he bestowed upon you in semesters past, and you guys retained all of it. You love moment and shear diagrams, you're really good at them, right? So if we take all of those concepts, right, where you guys learned how to take external forces, create free body diagrams, from that we can create internal force diagrams, which are shear and moments, right? We have two internal forces that are generated based on beam bending, right? Transverse loading on our beam, right? Long, slender member with loads that are transverse to the long axis of our member, okay? And so in beam bending, which is in chapter 8, we're interested, again, no new news here, right? We're looking at stress, strain, and deflection, right? We look at stress, we always want to relate. We're going to relate this to some allowable stress. Right. External forces create stress, right? We know stress is force over an area, so we need the geometry of our beam. Based on having stress, we know based on Hooke's law, right? Hooke's law gives us the relationship between stress, strain, and our modulus of elasticity. Based on those relationships, from stress we can get strain. Stress provides strain. From strain, we can get deflection, right? The definition of strain is the change in length over the original length, right? And using all three of those relationships, knowing stress, knowing strain, knowing Hooke's law, we then figured out some force deformation relationships, right? And if we have indeterminate systems, like in torsional systems and axial systems, right, it was this force deformation relationship and this relationship of deformation in our system, right? We had parallel systems, we had systems in series, we had systems that were connected, that were geometrically related to one another, right? Similar triangles and things. If one deflected, say, half an inch, the other one would deflect twice that much because it's twice as far from like a pivot, okay? So we're always looking at deflection because it provides equations for solving unknowns, which we'll get to in quite a while, and deflections in beams, we're going to relate that to an allowable deflection, okay? As we've talked about in this class, there's strength requirements. We want to make sure stuff is strong enough, but we also want to make sure that it doesn't deflect too much, right? Serviceability becomes an issue. We want to make sure that it's actually usable. And we talked about if this floor vibrated too much, right, it would become unusable, right? Like I couldn't be teaching here because someone's kicking their leg over there and it's vibrating this whole floor, right? So we can't have that. So we want to relate determined deflections back to allowable deflections to make sure things are stiff enough, they don't deflect too much, and so on and so forth, right? If Walmart's roof wasn't stiff enough, okay, and we had a huge water event like they're having in California, okay, you get what's called ponding, right? Center of the building starts deflecting and becomes just a pool. And then that pool collects more water, which collects more water, which collects more water, and then pretty soon it falls down, right? You get things like that, you would check for deflections to make sure that when it's loaded with 2 inches of water, it doesn't start creating this pool, right? A little big kiddie pool up there.
So is this a more of a civil engineering application?
No, beams are, I just happen to talk about buildings,
Okay.
right? So the beams are all over in mechanical systems as well, right? Automobiles have a lot of beams. It's just essentially a long member that has loads applied transverse to it, okay? An axle, like the axle housing would be a beam, essentially, right? You've got essentially 2 point loads and it's supported on the leaf springs, for instance, right? So there's bending in that axle housing. All right, so if we had a beam here, had 2 point loads on it, simply supported, okay? And it had a cross section that looked like this, and an upside down T. I'm going to replace this, and we're going to actually run some numbers here. So if we, instead of P, we had 2 kilonewtons of axial load, two kilonewton axial point loads, sorry, not axial, but point loads acting on this beam. Due to symmetry, we could run through our equations of equilibrium. We'd say P plus P minus 2 kilonewtons minus 2 kilonewtons. We could figure out what the reactions are, right? 2P equals 4 kilonewtons, or P equals 2 kilonewtons, right? 2 kilonewtons of reaction at D and 2 kilonewton reaction at A. And let's give some dimensions here. We're going to say this is 2.5 meters, this is 5 meters, and this is 2.5 meters. Okay. We're just running through our steps, our process, right, to developing our shear and moment diagrams. So once we had our external forces and our internal our external reactions, based on this, we could then develop our shear diagram, right, based on the rules, right? Discontinuity in the shear diagram is developed based on externally applied forces. So in this case, we have a reaction of 2 kilonewtons. We would jump up to P, or 2 kilonewtons of shear. That shear maintains a constant, okay, value until we get to another discontinuity, which is another applied load. So we have our point load acting at B, brings us back down to 0, shear is 0. We hit C, back down to 2 kilonewtons, right? Negative 2 kilonewtons now. If we look at the moment, right, we got 3 more rules associated with the moment. Well, the slope is the magnitude. The slope of the moment diagram is the magnitude of our shear. So in this case, the slope of that first triangle there is 2 kilonewtons, right? And it's going to be 2 kilonewtons until the shear changes. And when it changed, the slope would become what the magnitude of the shear diagram. Well, when the shear diagram is 0, the slope of our moment diagram is 0, right? 2 kilonewtons, positive 2 kilonewtons is our slope. Negative 2 kilonewtons, negative 2 kilonewtons is our slope. The magnitude at the end, right, or whatever point this is on our moment diagram, is the area underneath our shear diagram, right, up to that point. So in our case, right, it's P times A, or 2 kilonewtons times 2.5 meters, or we get 5 kilonewton meters, right? Everybody get that? So we've established our shear diagram and our moment diagram. These are essentially the internal forces that are acting in this beam based on these externally applied loads, right? The 2 point loads. So if we were given that, as we just mentioned, we're really interested in stress strain, and deflection, all of those things. So if we start by looking at stress, right, and we ask ourselves, what is sigma max at top and bottom of this member? Anyone know how to do this? So we might be able to just skip this section. No? Okay. So imagine this is this beam. We've got 2-point loads, kind of like a car lift, right? We've got the beam that's holding up the right side of our vehicle. We've got 2-point loads that are coming from our tires. They're acting on this beam that's running between our two posts on the side, right? So this is your MET version, Brennan, okay, of the beam. And this beam is this weird ass shape, okay? This wouldn't be the way that they do it. It'd be something that a tire could sit on, okay? But if it was an upside down T, we'd be really interested in the maximum stress, right? At the top or bottom, potentially, of this beam. Well, if we're working from stress to strain and then deflection, right? With deflection being our end goal, well, we can start by looking at, well, what do we know from the systems we already looked at, right? We've already gone through axial loading. We've already gone through torsional loading. So you remember for axial, deflection equals FL over AE, right? Which is essentially saying stress times L over E, right? In order to get this equation, we took stress, knowing F over A. We know Hooke's law, which relates stress and strain and modulus of elasticity. And then the definition of strain is our change in length, right? Deflection over our original length. So we combined all three of those equations into one, and we could solve for the deflection. So that's what we did for axial. If we were looking at twist, right? We had a torque-twist relationship. Twist was what we called phi, which is T, L over J, G, right? Torque times the length of the shaft. We only dealt with solid shafts or pipes, polar moment of inertia, right? And then our modulus, or shear modulus, I guess. Okay. So based on these, we know that deformation or twist is a function of stress, geometry, and material properties, right? In this case, E or G, right? The modulus of elasticity or the shear modulus, right? Well, our beams follow the same principle. But unfortunately, they have more complicated internal forces. Right, that's why we started with axial and then torsion, just getting you guys warmed up, okay? Just ready to go now. You totally understand what we've done. Looking forward to where we're going to be. Okay. So where do we start? Well, we start with forces, right? Everything that we've done in this class up till now, everything that we will do, we really need to understand our forces. Externally applied forces, internal forces that are a resultant of those externally applied loads. Those all come from free body diagrams, right? So where to start? We want to figure out what forces act on or within our beam, right? So that is free body diagram stuff. That's shear and moment diagram stuff. Right? Egen 2 something, right? 205? 3. Fuck. What's 205? You guys take 205? I just need to let go of that
I
one.
think
Then.
205 is the like mechanical and civil engineering version of
Statics? Oh, okay. So it's still statics, so it still works. All right? 205. 203. Okay, got it. 203. So we start with forces. You guys don't need more explanation about this, right? Done this a bunch. This is the 203 stuff. Okay. Now we want to figure out what stresses exist in the beam. And this is our current focus. Okay, this is going to take a while. This is why you don't have homework and quizzes this week, because it takes a while to get through this. Because unlike axial load, right, with an applied axial force, we get one internal force, right? For torsion, one external applied force, we get one internal applied force, right? Torque. For beams, you apply a transverse load. Now we have shear and moment that's acting on the inside of our beam. Okay? And so those create the stresses all themselves. Okay? So what stresses exist in the beam? Well, to find stresses, first need to know what's our external forces. We also need to figure out how is our internal transmission of force and stress. Right? So if we have these external forces, they create internal forces, right? Our shear and moment. Well, we need to know how those internal forces transmit force or stress throughout our cross section. Right? So I guess we go back to axial to bring it home. An external applied axial load, right, which created an internal axial force, right, creates this uniform stress across our cross section, right? That's normal to our applied load, right? Whereas torsion I'm not cheating here on my shapes. You can see that I'm human. Right? Linearly varying stress, right? We did this huge long derivation. You guys got to take a nap for 25 minutes or so. And we went through how that stress varied across the cross section, right? It was 0 at the center of our shaft, center of our circle. It's maximum at the max radius, right? So we had this linearly varying stress distribution based on essentially equilibrium, right? Because our applied force has to be equilibrated with a equal and opposite force, right? And an equal opposite force comes from stress, which acts over an area, right? Stress times area is a force, and that has to resist it, right? And so we need to know how is this force or stress transmitted throughout our cross section, and then finally, right, we need to know the geometry of our member.
Isn't that 3? Geometry of numbers?
Shit. Yes. Good call. Just making sure you guys are alive out there. Totally did that on purpose, huh? Okay. So we have to find stresses, right? We need to know first our external forces We then take those external forces, figure out our internal forces and or stresses and how those are distributed across the cross section. And then when we know those internal forces, we need to know the geometry, right? Area. Stress is force over an area. And so then we can finally get our stresses. So if we start by looking at external forces, and we continue to look at our same example where we have two kilonewtons. Right, this was 2, this was 2, this was 2.5, this was 5, this was 2.5. This was -2. Trust me, this will all make sense when we get to the end of all this. 5 kilonewton meters. Okay. So we have this car lift beam, car sitting on it. Okay. We've got our geometry as shown. Well, if we look at this sliver, right, if we cut out a section of our beam and it goes from point H to point K, right, and it's some length long. This could be 1 inch, this could be a foot, right? But if we look at some small increment of this beam, right, and we call it delta x, right, or a change in distance, and we pulled that out, right, and then I cheated and I drew a nice square. So, okay, so we have this section of beam that we pulled out, right? Pull that section of beam out based on our free body diagram, which gave us our reactions, right? We could draw then additional free body diagrams, right? Cutting it, method of sections. Or we could go through our rules, right, for developing our shear moment diagrams, which we did, okay? So at this section, we know the internal force that's applied to each of these faces is a positive moment, right? Positive moment of P times A, or 5 kilonewton meters, which is this guy right here. So if we took this piece of beam out, and we drew a free body diagram of it, right? It's gonna have these internal forces on it, right? Or 5 kilonewton meters. And 5 kilonewton meters, right? We know that it's positive moment. We know the sign convention for a positive moment should induce a smiley face, right? Real happy, this little section of beam. We got a positive moment drawn on both sides. Right? And this would be, you know, point H to H and K to K. Well, these internal moments result in the application. So let's do this. So moment results in application of normal forces in the member. So let's draw another picture to kind of show that. Got another nice beautiful square, right? If we draw our positive moment on one side, okay, we have our 5 kilonewton meter moment, positive moment on one side. Right? This little section of beam has to be in equilibrium, right? Anywhere we sliced it out of there, it can't continue to fly off into space. In order to make sure that it doesn't do that, forces need to be equal and opposite, right? So if we look at the other side of this, I'm going to draw what's called a neutral axis. Whoops. This is again H to H, K to K. This is some just all width of beam between our 2 point loads. We have our coordinates, X and Y, for drawing a free body diagram. Okay. So moment results in application of normal forces in the member. Okay? So in order to resist this applied moment, we create these internal forces, right? That are creating a couple or a moment about this neutral axis. Well, what is the neutral axis? The neutral axis is the point at which there is no stress, no strain in our member. Similar to what we had in torsion, right? Where we had zero stress at the midpoint, right? Because we had no strain. There's no deformation. As we moved our way out, that stress increases because our deformation increases. Similar behavior here, right? So we end up with these forces, okay? A force in compression and a force in tension, right? Equal and opposite. And they create a couple about what we call the neutral axis. Right? This is where our normal stress equals 0. And this always runs through, wow. And it always runs through the centroid of our cross section. Right? Our centroid of our cross section. You guys remember that from 203, right? So our internal applied moments create these forces, right? Above and below the neutral axis that create a couple about our point of zero stress or zero strain, which results or is a result of this linearly varying stress, right? Similar to what we have in torsion, right? Which starts at 0 at the neutral axis. Torsion started at 0 at a 0 radius, right? The center of our shaft. And its maximum out at the extreme 5, right? Above and below our neutral axis. All right. So let's step back and think about, this is where you guys are going to glaze over hard, okay? Right. But I stepped forward and gave you what the end result was, right? We get this linear distribution of stress. We have these forces that are applied above and below this neutral axis, right? Well, why is that? Well, if we looked at our beam, okay, we had our beam, it's a part of our car lift, okay? Car sitting on this beam. We have our shear moment diagram that we've already developed. Well, because of this loading, right, everybody can agree, I assume, this beam's going to deflect, right? It's going to deflect downward. So if we look at this little section or sliver of beam and zoomed in really closely, right, to this little section of beam that was deflecting between our 2 point loads, as we took our sliver out, we looked at the deflected shape, it'd have some curve to it, right? It'd have some curve to it. That curve, this guy here, rho, is what we call our radius of curvature. Right? So if we look at what we call our neutral surface, right? That's the point where there's no stress. And we looked at a small portion of this beam, okay? And it was deflected, right? So it was bent. And we looked out somewhere there'd be a center point for the curve that that little section of beam underwent, right? And so that's called our radius of curvature. Okay. Well, if we look at our little cross section, right? I talked about how this internal moment creates these internal stresses, right? That start at 0 at our neutral axis and increase linearly as we head outward. And we can say that we know force creates stress. Right? We know force creates stress. Then we can then relate stress to strain, right? We have Hooke's law, and then geometry. Right, to get deflections. All right, so if this beam undergoes bending, we're going to create stress. That stress creates strain, right, which is deformation. And we end up with a curvature, right? So let's start with strain, right? So strain, definition of strain, is the change in length over the overall length. Right? Well, if we have two lines here, right, we have our neutral axis, which we know is our delta x, right? And we know that there's no stress, which means there's no strain along this neutral axis. So if that was the original length of this block, right, we know that the top portion undergoes stress, which induces strain. And because we have curvature, right, the top is going to be squished, bottom is going to be trying to get pulled apart. And so if we had a new length, right, this originally would have looked like something like this. Right, that would have been the original shape. Would have been a square, rectangle. Now that we've induced stress, which induces strain, right? And we have this curvature associated with that, right? The deflected shape. That curvature is going to shorten up the top of this beam and lengthen up shorten up the top and lengthen up the bottom. So if we looked at a line that was a part of the top, right? We would have some different length, delta x, right? Delta x prime. Okay. We have this new length delta x prime. And that new length delta x prime, right, runs along a radius, new radius, of the radius of curvature, which goes to our neutral axis, minus whatever distance this line that we're looking at is above the neutral axis, right? We call this distance y. We've got distance y. So we're looking at a line that's within our cut beam that's a distance y up from our neutral axis, okay? That new curvature distance, right, is our initial radius of curvature, which is our neutral axis. Subtracted out our y distance, right? This is where it gets well, if we took a very small sliver of this beam, say delta x is small, that also means that this angle's very small, right? Even if you had a beam that deflected a lot, if you looked at a very small portion of that beam, right, the angle over which you are looking at this distance is super small, then the angle is going to be super small, right? And if you do that, you use small angle theorem, which essentially says that your arc length, which is the length of this little cut, is the radius to it, right? Is the length of your is the radius times the angle. It's essentially distance times angle equals length. So then we can relate how long each one of these lines are based on the angle and our radius. So that's what we're going to do. We're going to say now that delta x equals the radius of curvature times delta theta, which is essentially the length, right? The original length. If we go back up here, right? L here, that's this L here, right? Trying to develop the strain equation is what we're going for. Right? So the original length, we can all agree, is this delta x, right? It's our neutral surface. We know it's not going to get longer or shorter as it bends. That was the original length of the sliver we took. We decided that we're going to take a very small sliver. So that sliver is related to this radius times the angle. So we came up with this equation for the length. Well, we also need deformation, right? Well, the deformation is the change in length, right, of this line, for instance, right? We're going to look at this delta x prime. Our change in length is how much did we deviate, right? This was the original. So as we squeeze this section of beam, right, compress it, and make delta x prime smaller than delta x, I think we could all agree that the change in deformation would be this distance, right, from the original shape to this new shape. On both sides, it's going to be symmetrical. We have the same amount of loading on both sides. So we have this delta 1 and delta 2. So if that's the case, our change in length is really delta 1 plus delta 2, right? Which, if we're looking at our two lines here, delta 1 plus delta 2 is really just the change in length between our original length, right, delta x, and this new length, delta x prime. Right? Delta x prime plus delta 1 plus delta 2 is delta x. So the difference between the two is essentially our deformation. So we could say delta x prime minus delta x. Right?
Wouldn't it be delta x minus delta x prime?
No, because we need the sign out of it. We need to know that this is negative. Because it's under compression, it's getting smaller. Right? This is a negative number. And if you remember, change in length over overall length, change in length is, we're getting smaller, so it needs to be negative. So we use the smaller minus the larger. Okay. So we can now plug things in, knowing our small angle relationship. We can rewrite this equation based on this small angle relationship between the radius and the angle, right? So radius of curvature times the change in angle, that gives us the length of our neutral axis. If we use this new radius of curvature or the radius of curvature to whatever line we're looking at, right, that's above our neutral axis, that length of that line is the angle times that radius, right? Well, we know that strain, change in length over the original length. So we end up getting this huge ass equation. Does something like this. All over length. Well, we knew that was our radius of curvature, right? Up above we have length. So we're gonna put length down here. We have deformation. We're gonna figure out what the strain is in our beam. Yeah.
In that first deformation equation, is the second row times the change in theta divided by the change in x? What is that sign?
Oh, no. So this is just saying, sorry for that. Don't confuse that. This is saying that all of this, right? All of this stuff is delta x prime. All of this stuff is delta x.
I see.
Yeah,
Thank you.
thanks for clarifying that. I'm sure you were not alone on that one. Okay. So we come up with a super long equation for strain. Well, when it boils down to it, you can simplify it. You get strain equals negative 1 over the radius of curvature times that distance y, right? Which y is the distance from our neutral axis to our arbitrary line, right? Or point within our cross section that we're looking at. What is our change in length of that piece of material? All right. Sick. Okay. So we have also, as we know, we use our three concepts of strain, Hooke's law, and our definition of stress, right? Force over an area. Well, if we look at Hooke's law, it says stress is strain times the modulus of elasticity. We can then substitute in and just get that modulus of elasticity times the distance up from our neutral axis divided by the radius of curvature gives us the stress, right, at any given distance up or down from this neutral axis, right? Essentially plotting this stress distribution, right? And you know it's linear because all of the factors in there are linear, right? It's just a function of how far up you are from the neutral axis times the modulus of elasticity divided by the radius of curvature, right? So we would get a linear distribution, which is what we see here. Validates our initial assumption, right? Something to note here, if you have a positive radius of curvature and a positive distance from your neutral axis, positive being upward, and this is positive y, this would be a negative y. Radius of curvature, right? This is a positive radius of curvature. If it flips over the other way and say it was, humping, right, or a negative bending moment, be a negative radius of curvature. But if we have a positive radius of curvature, positive y, we get negative strain. And we know from dealing with axial loading, right, a negative strain is compression, right? Because a negative strain, plugging that into Hooke's law, you're going to get a negative stress. Negative stress is compressive stress, right? So you thought that going through all this was painful. If we really wanted to, we could go through all the integrating. Right? Or essentially summing. That's all you're doing with integrals is summing up over something. So moment, if we sum up all the moments over the area. Right, so if we look at this cross section, you know, each one of these stresses acts over some little bit of area, right? So if you took each one of those incremental little increases in stress, you multiply it by a small little area over which it acts, you figured out what the force was, you'd have a series of all these forces, right, that are acting on our cross section. So if you ran an integral to figure out what's the overall moment that's acting there, you end up getting this resultant as the moment equals E I, or your moment of inertia over your radius of curvature. Oh, this is getting really small. And lastly, we're going to kick this up here to make it bigger for you guys. You get stress equals negative my over Iz. Okay? Essentially take this equation, once you sum moments, you get this equation for the moment across the cross-section. The modulus of elasticity times the moment of inertia divided by the radius of curvature. Well, if you solve this guy for, say, the radius of curvature and plug it in here, you end up with this equation here. This is the lock-stock bending stress equation, almost dedicate to memory sort of thing. Okay, stress is my over I, right? Negative my over I. So we've got this, yeah?
That z is a subscript, but in the y is not, correct?
Yes.
Okay.
Sorry, yeah. Y is this y. Moment is your applied internal moment in the cross section. And I is your moment of inertia about what we would call the z-axis. Right? Which is running in and out of the page at the neutral axis. Right? X is running down the length of our member, Y is running vertical, and then Z is running outward of the page. Okay? So if we had a steel I-beam that ran something like this, right? It was running between 2 points. Our Y-axis is vertical. Our X-axis is running down the length of our beam. And the Z-axis is the one that's crossing our cross-section, right? Sticking out at you guys. It's what our member is going to be bending about, is our Z-axis. So we want to know what the stiffness or resistance to rotation, as you guys did in eGen 203, right? You guys figured out moment of inertia. And so you need to know how resistive this section is to rotation, how stiff is it, and that affects what kind of stresses you'll see within the cross-section. All right. All right. So as I mentioned, we had 1, 2, and 3, right? We had internal forces. Well, we had 1, 2, and 2. We had external forces, internal transmission of force and stress. So we just figured that out, right? We had this linear change in stress, my over I. So for a given applied moment and a given cross-sectional stiffness or moment of inertia, right, our stress is linear from our neutral axis outward as a function of how far out we are from that neutral axis. Right? And then finally, we need to figure out the geometry of the member, right? Because my over I, one, you need to know where the neutral axis or the centroid is of our cross-section. That sets the groundwork for where y is counted from, right? Above or below. And then we also need to know how resistive our cross-section is to bending. So we need to know geometry. So to determine stress distribution, need to understand, oh, there's no paper there. Understand the geometry of the area transmitting the force. most notably. We need the centroid, and we need the moment of inertia. Right. Well, if we look at centroid first, okay. The definition of the centroid, or y bar in this case, equals summation y sub I, a sub I, over summation a sub I, right? So we pick a reference axis, you did in 203. You sum up all of the areas, okay, that act, essentially the first moment of your area is what the moment of inertia is, right? So we take the distance to the centroid of whatever area you're looking at times its area. And we do that for every piece of our shape, right, from our reference axis. And we divide that by the total area of our cross-section. Okay? So if we broke our upside down T-beam, right, our little car lift beam, into two pieces, I'd break it up into these two pieces. You can break it up into as many pieces as you wanted to, okay? I'm going to break it up into these two pieces. We would need to know, right, the centroid of our piece. In this case, we're going to use millimeters. Also interested in the area of our piece of interest. And then finally, right, we need y times a, bless you. Okay. So kind of need these three components of each of our broken up areas. So if we look at our cross section though, we need to start with a reference axis. So I'm going to call that Z, vertical axis Y. I placed the Z axis right here. You could have placed it anywhere in this cross section, right? Anywhere in that cross section. It would just change some of the values, but you're going to get the same location for the centroid. Okay. Wednesday, I guess.